Hello everyone. So in this video we are going to talk about extreme values. We're going to focus on maximum and minimum values. So when we talk about an extreme value, um, or we can call them extrema, we're looking for maximums and minimums. And we could think about this in two ways. We could talk about what's called a local maximin, and we could talk about an absolute maximin. So let's look at a couple of generic functions. I'll call this guy f of x, and I'll call this one down here g of x. So we look at f of x. This graph has a maximum here, and it has a minimum down here. So notice, and I'm not sure what's going on with my computer. Let's see. Notice maximum here, minimum here. Okay, notice that this is a max value. Okay, but it's not the highest point on the graph because the range of this function goes up to positive infinity. So it's a high point, but it's not the highest point on the graph. Same thing with this. It's a low point, but it's not the lowest point on the graph. So when we're talking about local maxima and local minima or local extrema, then we're talking about places that are a high point or a low point on the graph. And that's what our function is saying. If we have or that's what our definition is saying. If we have a function f that has a local maximum at some point c, then there exists some kind of open interval I containing c such that I is contained within the domain of f, and f of c is greater than f of x for all of the x values in that interval. So what that's saying here is if we have a maximum at this point c, we could think about some kind of small interval around that x value so that this y value is the biggest y value within that interval. So we're not looking at the entire picture, we're just looking at a small portion of the picture. Same thing is going to be true when we talk about the local minimum. We're still talking about some kind of small interval that contains our value. I'll call this C1 and this one will be C2. So we're looking at a small interval around here where that y value is the smallest y value in that particular interval. And that's going to be a little bit different than when we talk about absolute mins and maxes, because now we're talking about the highest point or the lowest point on the graph. So we say f has an absolute maximum on I at c if f of c is greater than f or greater than or equal to f of x for all x in that interval. So if we're looking at here, we're talking about absolute extrema. I'll call this C. We'll call this C3, just not so we don't get it confused with those C's. That is the highest point that's on that graph. So we do not have a y value that's bigger than that. So we would say this is an absolute maximum, whereas this guy is a local max. So now let's look at the extreme value theorem. If f is a continuous function on a closed bounded interval from a to b, then there's a point in AB at which f has an absolute maximum, and where there is also going to be an absolute minimum. So what that's saying, let's go back to our generic function here. What if we don't want everywhere f is defined? What if we just want a piece of this graph? So this is the function f of x again. And what if we want to look at this just from here to here? So my graph is not everything to infinity, but just from here to here. If we were to bound that interval and look at a closed interval, and that's important, we have to have a closed interval. It cannot be an open interval for this theorem to work. Then what this theorem says is that we are guaranteed to have a maximum and a minimum on that interval. And on this one, we can see the maximum would happen here, and that minimum, that looks like it's a little bit lower to me, would happen here. And that would give us absolute maxes and mins. So, but just by looking at a portion of that graph. So then the question becomes, how do I find it? How do I figure out where the maxes and mins are going to happen? And that's where this idea of a critical number is going to come in. We're going to let C be some point inside the domain. We have a critical number if the derivative is equal to 0 or if that derivative is undefined at a particular C value. So there's two conditions we have to check. Define critical points. We're going to set the derivative equal to 0 and figure out where the function is undefined. If there is a max or min, it must happen at a critical point. I was talking about a local. I call these critical numbers. You're going to see me use the abbreviation CN here. So let's look at a few examples. For each of the following functions, let's figure out critical points. So to find a critical number, we're going to take the derivative and we're going to set it equal to 0. So if I take this derivative, 1/3 times 3 would be a 1. So this is a 1x squared minus. If I take the derivative of that second term, I'm going to get a minus 5x. And then the derivative of the last term is 4. So we're going to set this guy equal to 0. So x is going to be 4 and 1. So these are our critical numbers. Okay, now you also have to think about where is the function, the derivative undefined. And in this case, that derivative is a polynomial, so it's never undefined. Let's look at this one. So we're going to take our derivative. So we're going to use chain rule, bring that exponent down, subtract 1 from the exponent, take the derivative of the inside. I'm going to clean this up. So this is 6 times x squared minus 1 quantity squared. So we're going to set it equal to 0. So we have 6 times x is equal to 0 and x squared minus 1 quantity squared is equal to 0. So we're going to get 0 here. I take the square root of both sides and then set that equal to 0. You get plus and minus 1. So these are my critical numbers. If we have a max or a min, it's got to happen there. And then we're going to do the same thing for part C. This is going to be a quotient rule. Quotient rule says it's the bottom times the derivative of the top minus the top times the derivative of the bottom. Oops. However, the bottom squared. So let's clean this up. We have 4 plus 4x squared minus 8x squared all over 1 plus x squared quantity squared. So we have 4 minus 4x squared over 1 plus x squared quantity squared. And we're going to set that guy equal to 0. We're going to have 0 equals 4 minus 4x squared. So x is going to be equal to plus or minus 1. So these are critical numbers. We also need to think about where is the derivative undefined. So that's where we would set that denominator equal to 0. And notice there's not a place this is undefined under the real numbers. I take the square root of -1, I'm going to get plus and minus I. And we are focused on real numbers in this class, so there's not a place that derivative is undefined. So the only critical numbers we have are at positive and -1. So we can do the same thing for this one. We're going to take that derivative and we're going to set it equal to 0. And this is where you may want to pause the video, try it, and then come back and check your answer. I have 3x squared minus x minus 2. I'm going to set that equal to 0. Let's see if this factors. So I'll get 3x squared minus 3x plus 2x gives me that minus x there, and then minus 1. So set each factor equal to 0. So x is going to be equal to 1 and -2/3. So these are my critical numbers. So if we have a maximum or a minimum, it's going to happen at one of those critical numbers. And we'll talk about in the next section, how do I know if it's a max or a min? And we're going to get into something called the first derivative test. So that's what's coming up in the next video. But before we do that, let's examine absolute extrema a little bit closer. For absolute extrema, we don't need to think about the first derivative test. So how do we find absolute extrema? That's always going to happen. We're thinking about a closed interval here. So we're not thinking about the function on its entire domain. We're thinking about just a small piece of the function. So we're going to first find all of our critical points. And I do this in a different order. So I'm going to find all those critical points first. And then I need to find y values that's associated with everything. So we're going to find y values at the endpoints. And we're going to find y values for our critical numbers. And then we're going to compare. The biggest y value is going to be the maximum, and the smallest y value is going to be the minimum. If we're looking at absolute extrema on a closed bounded interval, then we're guaranteed, remember, extreme value theorem said we're guaranteed to have our max or a min. And it has to happen either at a critical number or it has to happen at an endpoint. Going back to our picture that we drew earlier here, when we found critical numbers, we would find this critical number and this critical number by taking that derivative and setting it equal to 0. But that would not tell us anything about the endpoints. So to know if we have a maximum or a minimum and where it's located on a closed interval, we would just find y values and then compare the y values. And we would do that for the critical points, which would be in here, and then we would do it for the endpoints. So that's our approach here. So let's look at this one. We have this function, f of x equals -x squared plus 3x minus 2. We're looking at the closed interval from 1 to 3. So this is a quadratic, but we're not looking over the entire rails. We're just looking at a piece of this. So let's find critical numbers. To find a critical number, we're going to take that derivative and we're going to set it equal to 0. So minus 2x plus 3 is our derivative. And if I set that equal to 0, x is going to be equal to 3/2. And then we're going to find y values. So we're going to plug in 3/2. And then we're going to plug in our endpoints. Plug in 1, plug in 3. This is going to help us find absolute extrema. And I'm going to plug these numbers in online to find y values. We plug it into the original function. I'm using my graphing calculator off to the side. When I plug in that 3/2, I got a 0.25. When I plug in 1, I get 0. And when I plug in 3, I get -2. So my biggest Y value is going to be the absolute maximum. So my biggest Y value here is at the point 3/2, 0.25 or 1/4. And the smallest Y value is happening here. So this is the absolute minimum. And that's happening at the point 3, -2. So you may want to pause the video and try the next problem. So we're going to find critical numbers. So to find a critical number, we're going to take that derivative and set it equal to 0. We're going to have 2x minus 3 times 2/3, which is a minus 2, x to the negative 1/3. Let's set that guy equal to 0. X to the negative 1/3. Let's pull out a 2 also. So we can always pull out that smallest exponent they have in common. And that's going to leave us here with a 4/3. Why? Because when I multiply this back, x to the negative 1/3 times x to the 4/3 would give me an x to the first. And we're going to have a minus 1. That's going to be equal to 0. So here's my derivative, 2 times x to the 4/3 minus 1 over x to the 1/3. And that's going to be equal to 0. So let's figure out what our critical numbers are. We're going to take this derivative, set it equal to 0. I've already done that. Multiply both sides by that denominator. That's going to give me this. Divide by 2. Move the 1. Raise this to the 3/4 power. What I do to one side, I got to do to the other. So x is going to be equal to 1 to the 3/4 power, which is just 1. So there's a critical number. But we also need to think about where that derivative is undefined. Hold on 1 minute. Let me think about this a little bit more. This is really the 4th root of 1 cubed, which is the 4th root of 1. Since this is an even root, we're going to get a plus and minus 1 there. So that was a little bit tricky. I had to think about that one for a second. So we've got critical numbers at plus and minus 1, but we need to know where also that derivative is undefined. So this derivative is undefined at x equals 0, because if I were to plug a 0 in to that derivative, I'm dividing by 0. So that's going to be a critical number also. So we've got 3 critical numbers to think about. So I'm going to list them right here. 0, 1, and -1. So now we're going to find y values associated with each of those. And we're also going to look at the endpoints at 0 and 2. So I've already got 0 there. I'm just going to plug the 2 in here. To find the y values, it goes back into that original function. So again, I'm going to do that off camera. So this is the function x squared minus 3x to the 2/3. When I plug in 0, I get 0. When I plug in 1, I get -2. When I plug in -1, I get -2. But notice -1 is not even on that interval, so we really don't even need to think about it. It's not on that interval. And then when I plug in 2, I got -0.7622. So my biggest y value is 0, so this point is the absolute maximum, and that's happening at the origin 0, 0. And then my smallest y value is -2, which means this is the absolute minimum happening at the point 1, -2. Let's do one more. We want to find the absolute max and absolute minimum for x squared minus 4x plus 3 over the interval from 1 to 4. And this is where you may want to pause the video, try it, and come back and check your answer. So I'm going to take that derivative. So I get 2x minus 4. I'm going to set it equal to 0. So x is going to be 2. So there's my critical number. There's not a place that the derivative is undefined. So now that we have the critical number, we're going to compare y values. So we're going to plug in the critical number, and then we're going to plug in our endpoints, which are 1 and 4. And remember, to find y values, they're going back into the original function. So again, I'm doing that off screen. So I have x squared minus 4x plus 3. When I plug in the 2, I get a -1. When I plug in 1, my y value is 0, and when I plug in 4, my y value is 3. So this is my minimum y value, so this is going to be my absolute minimum. This is the biggest y value, so this corresponds to the absolute maximum. So with absolute extrema, you find critical values, and then we really only care about the ones on the interval. And then we just test y values. We figure out what y value corresponds to the critical values and the endpoints. Biggest one is going to be the max, smallest one is going to be the min. In the next section, we'll get into the first derivative test, which will help us look at local extrema.